Hello there. This is week 11 and Tuesday lecture, and we're going to do maximum distortion energy criteria. Okay, so we actually call von Mises. So I'm just going to write the maximum distortion energy criterion, and this is what we usually call is based on the name we usually know is called von Mises or von Mises, and it's for ductile material. Only when you have ductile material you can use this criteria, not for anything else. So it's same as Tresca. So but it's based on energy. It's based on energy required to change the shape of the material. Okay, so it's an energy base, and the limitation is a distortion energy per unit volume right under plane stress condition. So you'll be wondering, what do we mean by plane stress condition? So in plane stress condition, okay, one of the normal stress direction is equal to 0. Okay. So it is only applicable in plane strain direction. So distortion energy, so UD is distortion energy okay. So I'm going to write a form of the distortion energy defined by von Mises is UD is equal to 1 over 6G, okay, bracket stress A squared minus stress A stress B plus by stress B squared. Okay, so this equation you see over here is our equation number 1. Okay, and where stress A and B are the principal stresses, means zero shear, and G, you see over there, is the modulus of rigidity. Okay, so where do you see G, and is where you have shear stress is equal to gamma G. Okay, so this is where you've seen it before. So this is shear stress this over here is your shear strain, and over here is your modulus of rigidity. Okay. So now, in terms of shear stress, or in terms of plane stress, so I'm going to draw a 3D element to elaborate further. So we have our element or transformation x, y, and we have over here z. And if we were to draw a cube, so this is our cube. Okay, so this is our element or cube. So we know so this is our stress x, and then we have our stress y, and then we have another stress z, and then we will have our this is our shear xy, and this is our shear yx, and then we have a next one, which is this is our shear yz, and this is, sorry, shear is a arrow, oops. Okay, so this should not be an arrow that looks like this. It should be I'm going to cancel this. Okay, the shear should look like this. Okay, so this shear z y direction, and then you have another direction. So this is your shear x plane z direction, shear z plane x direction. Okay, so when we are under the plane stress situation, so plane stress usually states that stress z is equal to 0, or the loading is in 2D. Okay, 2D loading situation. Or configuration. So when there's two-dimensional loading configuration, the only way for that situation to be true is shear sz must be equal to shear zx and has to be equal to 0, and shear zy is equal to shear yz is equal to 0, because you have nothing in the what? In the z direction. So now when that's the case, you come back to, you only need to draw things in 2D now. Okay, no need to express in 3D. That's why in plane stress situation is also known as a 2D loading situation. So you see, if what you see is what we have left with, we are near left with stress x, stress in the y, and you're now only left in the shear in the xy and shear in the yx direction. The rest is equal to what? 0. Okay. So the maximum shear stress, in this case, the maximum shear stress will be on the xy plane. Okay, so which is this plane over here, which reflect on this element. Okay, so from equation number 1, so from here we know that from equation number 1, right, we let stress A to be equal to stress yield. And then we let stress B is equal to 0, where stress Y is the yield stress. So why we make this decision? Okay, why von Mises make this decision? Okay, so if we were to draw this in 3D mode circle now, alright, we will draw this in 3D mode circle now. So we know, so assuming that we are sketching for this element over here, so this is our point X. Okay, so this will be in our point X. This will be our point Y. So we draw a 3D mode circle. There's one point here. This is one point here. Right, so we know stress X is tensile. Right, we know stress X is tensile at this point. We know stress Y is also at tensile. Right. So we know stress X is in tensile, stress Y, so I push it closer, I don't have enough space. And then we have our shear. Okay, so we have our shear somewhere around here. So this is our shear. Alright, then we have another shear over here. So what we see over here is you have your point X over here. Okay, so tensile. So this is your shear going in the clockwise direction, and then your shear going in the anti-clockwise direction. Right. So from here we have a point over here, or it was assumed that we have a point over here. So stress X positive, point X, and this is our point Y. And this is one of our circle. Okay. Right. So this is one of our circle. And then from here we can draw our 1 mole circle. So this is one of the circle. So I'm going to sketch this out. I'm going to eyeball this. Not going to be perfect, but it's good enough. Okay. So I think I need to make it more. Okay, so from here, right, we know that this is our stress A, and over here, this point over here will be our Z point, and this is the other circle. Okay, this is our circle. And then we have another circle coming in, which is our bigger circle. Okay, so this is 2, 4, 4 and a bit. Alright. So this is our third circle. Right, so from here, that's what von Mises assume. Okay, that one of our value over here, so this correspond to our stress B is equal to 0. Okay, so that's why his analysis, right, his analysis has to be Z is equal to 0. And I think I make a mistake down here. The maximum shear is not necessary to be on the. Okay, so I'm going to get it. I do apologize, that's not true. So we know that the XY, right, we now know that stress A correspond to our stress Y based on von Mises criteria, and stress B is equal to 0. So that's how he made the assumption, and that's why it's important that stress Z must be equal to 0, and that is only possible through what? Plane stress condition. Okay, that is only possible for plane stress condition. So when that's the case, he came out with an expression now. So by looking at that circle, okay, at the 3D mole circle, yeah, earlier when I deleted that statement is not true. That's why it's so important to check where is your maximum shearing stress, either is it in plane or out plane. Okay, so I got it wrong earlier. So now you can now write, so if that's the case, equation 1, okay, equation 1 becomes, so we put it energy due to distortion energy at yield is equal to 1 over 6g, right? And then this will be equal to stress y squared, right, minus by stress y multiplied by 0 plus by 0 squared. So you come up with an expression where the yield will occur at sy squared over 6g. So this expression itself is known as von Mises, okay, von Mises yield criterion. Okay, right. I'll come back again to do another video on the limits of this von Mises criteria.